things into context. Cosmology, over the past 20 years, has made the transition to what is called precision cosmology. So precision cosmology because many of the parameters are known with exquisite precision. So, and also it has moved from a data-starved science, you haven't seen that, to what is called a data-driven science. From where, you could do a galaxy correlation function with a few hundred galaxies to the point that you're doing millions. As a result of this, cosmology has a standard model, which is called the standard cosmological model. For friends, it's the vanilla Landesian. Do you know what this model is? Okay, good. This, for our purposes right now, this model needs only a few parameters, 6 parameters basically, to describe the origin, composition, and evolution of the universe. There is a big difference between modeling and understanding, and I don't need to say anything more about that. And so, here as an example, this is Planck, this is the zoological size survey, and you heard about this already. So, in this sense, cosmology is special. Cosmology is special because we don't really make experiments, we only make observations. In any other science, you do your experiment and you can tinker with it. In cosmology, you cannot. You just observe what is out there. So basically, you want to use the universe, the entire universe as a detector, but the detector is given. You don't necessarily know its property because you haven't built it. And the course of cosmology is that we only have one observable universe. There may be more out there, but that's all we can see and we observe. And also we can only make observation and only of the observable universe. And so what we do, we feed models that is constrained numerical value of a series of parameters to the observations, which means that any statement is going to be dependent on the model we choose. Also, non-linearities and gastrophysics. Now, gastrophysics is not a typo. It's actually a slang jargon for people that work in the field. These are processes that are either nonlinear or complex or poorly understood, that you can't really model nicely and cleanly from the first principle. Also, different observations are more or less trustable. Now, all the observations that will be presented in the school are trustable. So if you think about, I like to think about standard credit rating for countries, so the observations that will be presented here are AAA, don't worry. But the results will depend on the data that you are willing to consider. And so this bringing the whole issue of robustness of the results. On the other hand, this is also a blessing, because we, in principle, we can't observe all there is to observe. If you only have one observable universe, in principle you can see all there is to see. And actually, we almost do. In this sense, the future is bright. And this is what sometimes I call ultimate survey. The moment you observe something that is very close to observing what there is to observe, there's no point to observe more. It basically saturated the amount of information that can be extracted. In some sense, the future is here because for primary temperature anisotropy of the cosmic microenvironment, the Planck results are basically the ultimate experiment. I say primary, okay? Temperature. So there's more to do, but for primary and temperature, we have a ultimate experiment. And so, basically, from observation of the observed or observable universe, now we want to make inferences about the properties of the entire universe. Now, the entire universe, what is called cosmology, is an ensemble of all possible observed or observable universe. Now, I'm not talking about the multiverse here. It's just that if what you see is just a small part of all that there is out there, you are forced to think in terms of that. Is everything clear so far? Imagine the universe is very, very big, and you are sitting in a place and you can only see a small patch of it. But, you know, you could be an alien sitting on a faraway galaxy somewhere else and try to make the observations, right? You don't necessarily see exactly the same thing that you see by sitting here and now. So, our observed universe is somewhat like a random draw of all these other aliens that could have observed all the patches of the universe. And so the assumption we make is that what you can see is a fair sample, is not, you know, a very particular corner of this very big universe that you can't see, and then you want to do inference. So no wonder that the majority of cosmologists are Bayesian, because you want to do inference, and Bayes gives you the means to do inference. Okay. So let's go and recap again what we heard this morning about probabilities. Probability could be interpreted as a frequencies, you know, number of events over the number of trials. Dice. You throw the dice and you say what probability you're getting 1, I try 2 times and see how many times I get 1. But also, so there is a different interpretation of probability, and that's the whole sheer small big battle between frequencies and Bayesian, though today it's not much more of a big battle, basically, at least. Physicists and astrophysicists have some tools, and they decide to use the ones that are more useful, more adept, or more easy for the problem. But anyway, so for frequencies, events are frequencies of occurrence, and probability are defined as the quantity obtained in the limit of the number of independent trials very largely. But Bayesian interpret probability as degree of belief in an hypothesis. And so they use judgment, prior information, probability theory, etc. But that's exactly what allows you to do inference about it. So Bayesian and frequentists don't criticize each other, but many physicists take a more pragmatic approach about what to use. Okay, so the challenge. I say that cosmology has entered the precision era, that a lot of data came along, and many more data will come along in the next few days, a few years. So cosmology will enter what's called the big data era. And this, of course, bring in the name of statistical cosmology, and precision cosmology was just the beginning of this. So what's important, and I'm going to say this here and probably not go back to this a lot during these classes, but it's important to put this out there. What's important is not how small your error bars are around a particular measurement, but how much they get casted, and not by you who made the measurement, but by somebody else. So in the error bars, there should be the statistical error, but there should be also other type of error that are not statistical error, that are called systematic errors. What we are going to be talking about in these lectures is exclusively about statistical error, but keep in mind that reporting the statistical error may not be the full story. When your statistical error is very large and any other error is small, it doesn't matter, but as the data set grows and the statistical error becomes smaller and smaller and smaller, then any other kind of small mistake you may make may be extremely. Okay? So what is all about? You have the data here, you make some measurement, you also have this cosmic variance, the fact that you observe a small part of this entire universe, and then you want to know about models and model parameters. Is it lambda CDM, how much lambda there is, maybe the cosmological constant is not a cosmological constant, what the heck is it some basis model, with some equation of state parameters, etc. Okay. So, since we've been talking a lot about probability, then we have introduced some notation, for example, the concept of a random variable. Let's say that the random variable is x, and I describe X with its probability distribution, P of X. So for example, X could be that you do repeated measurement of something, and have some error associated to it, and at the end you have P of X. This probability distribution has some properties. It's non-negative. It's a real number for all real value of the argument. And it's normalized so that it integrates with it. And then you can write some other rules that for totally exclusive event, the probability of getting x1 and x1 and x2, x1 and plus x2 is probability of x1 and x2. And this is what I'm doing like that. So what could be some random variable which is not associated with the probability distribution if you get given some cosmological data? Can you think of examples? Right. For example, you have your matter distribution. You decide to discretize your space to some sort of grid, and then compute the density at each point, and that density is your axis delta, and then your PDS is probability distribution. Another example would be, for example, the temperature that you see in the sky in a pixel. We have seen the colorful Planck map. That would also be one example. Okay, and in general, the probability of A and B is the probability of A times the probability of B given A, and the probability of B and A is the probability of B times the probability of A given B. And we've seen some example of this morning, right? Verde and then kind of thing. So for independent event, the probability of A and B is the probability of A and the probability of B. You may want to produce some example of this last case. Can you think of an example?
So an X is independent each row is a plus one.
How about the cosmology?
Assume there are independent measurements in very opposite directions.
Oh, so that's an interesting statement, because you say I take two very separate points in the sky, and I say I'm going to do two independent measurements. So what do you mean by two independent measurements? You have two different experiments that look at these two pieces of the sky, or maybe the same experiment, which noise, it's uncorrelated in time.
Yeah, I think that correlates with the same experiment. In correlation, like in the same experiment.
So you have the same experiment, and then you assume, say, that the noise of the experiment at one time, the noise of the experiment at time 2, have nothing to do with each other, they are uncorrelated, and they observe here and observe there, and I say that they are independent measurements. Is that what we are saying? Okay. What happens if there is an underlying process, however, that makes the actual measurements in these two different points as not being independent? Then you have two components, right? You have your component of your noise of the experiment that is independent and the underlying component that is not. So, for example, in the limit where you are dominated by the noise of your experiments, then you can say, well, this kind of reasoning is being done all the time when you are actually analyzing data. You say, if you are in the noise-dominated regime and the noise behaves like you say, then I can take this sort of approximation. Okay, good. Everybody's clear about this? Okay. So, you may also want to add another property of the probability, that is the probability of A. If you know the probability of A and B, it's the probability of A and B sum over or integrated over or cost of B. Does this make sense? This will be useful later when we talk about marginalization. Okay, so what do we want here? Then this brings us natural to Bayes theorem, or no, not again. Here it is, using a different notation. The probability of an hypothesis given the data is what we all have seen, I'm sure, in some lab somewhere as an undergrad. The probability of the data given the hypothesis, corrected by the prior, and corrected by these things, which usually we completely forget, just as one and don't care about it, unless we arrive to the advanced part of this course. Now, how do we get from here? Well, we simply use this, that was in the previous slide, and there's a posterior, there's a prior, there's the likelihood, and we just derive that. But there is a fundamental difference here because at this point we can't do inference. So one is the data and the other one is the hypothesis itself. So, being made and appear, you may treat them like data and everybody would agree that it's a data, while here, one of them is actually an hypothesis, a model. Okay, so the question for you is how do you choose your value? And now this is not a question for which I want to answer now, because there's no simple answer. It's an open question, you should know it's an open question, and as Alan said, Bayesian inference is completely deterministic the moment you choose your value. You should always declare your value, but how you choose it, it's a little bit arbitrary. So that's the other question. Drawbacks. So you may decide to do an analysis by saying, well, I want to measure the tensor to scalar ratio. That is, the amount of primordial gravity waves that were produced by inflation. And that's the tensor to scalar ratio parameter, it's called R. Maybe you remember a couple of years ago there was a big press release about having seen the twirl from the Verde of the universe, from the bicep to. That's what they claimed was the time. So that's the little R they're discussing. So some people like to just say each value of R is equally likely. So use a uniform prior number. Some other people say, oh, hang on a second, the tensor to scalar ratio cannot be negative. So I should not use flat prior or uniform prior. This quantity, I should use log of that quantity. It's fine. Other things is tau, the optical depth of the last scattering surface. You can decide to use tau as your parameter and uniform value of tau. But when the first till say 2007, 2010 CD data were being analyzed, you realize that actually a more reasonable choice would actually use the variable and sample uniformly the variable e to the minus 2 tau. Basically because the effect on the observable, on the primary observable that give you the most signal to noise, which is the CMB temperature, depends linearly on this rather than on this. So maybe this is the type you should choose. Or you can say, well, no, tau cannot be negative, so maybe you should use log. So sometimes you find yourself trying to compare the probability of x with the probability of a function of x. And the posterior, or whether you use a Unicode for prior on this or on that, may actually be fair because of this relation. And now I'm going to skip one slide with the solution of how to compare the one with the other one, and I'm going to show you an example. The example I want to show you is this. So let's figure out what's going on here. This is from the first year WMAP data. That's back in 2003. I know it's ages ago. This is omega matter versus omega lambda. And this is cosmometric background data. Only the dark region is the 68% confidence region, and we'll talk about later on exactly what that is, but you have the claim from this paper is that you have 68% probability that the true value in these big other patches of the universe, of which we just observed one random sample, lies here, and we have 95.4% that is actually lies there. And this is from this reference figure 13. So you may want, if you are not familiar with these references, you may want to try to bring them up on your screen, because then I'm going to ask you something about these references. Or at least, one in your group brings it up in the laptop and the other one reads, listen what I'm saying next, and then bring up on the laptop the other thing. This here is from the WMAP 3 years data results. And the orange contour is cosmometric background data plus the measurement of the Hubble constant by HST. So we are not concentrated on this, but we are concentrated on the transparent one, which is again is WMAP. This is the reference, and this is figure 21. Now, that's 0.6, and that's 0.6. Look, 68% confidence region doesn't close at 0.6, it keeps on going and going and going. While here, at 0.6, the one with the 68% confidence region is not there, it's closed. So how can it be that I added more data, and quite a bit more data? That was 1 year, that was 3 years of observation. That's a lot more data. It's 3 times, the data in the temperature, the power spectrum gets squared, so it's difference even more. That that's worse. These are the posterior. The analysis was done as it is standard in cosmology using Bayesian inference. So what do you think is going on?
Well, the prior change?
Yeah, exactly. The prior is changed. So if you're looking at the paper, I have my note here, the key for the 2007 paper is the equation 2, while the key for the 2003 paper is actually in equation 25 on a different paper. So that's really bad practice. It wouldn't go to a referee these days. We made it to the referee report at that time. We wouldn't fly now. You go to declare your prior when you present your results, right? And not declare your prior in a different paper. So the prior is changed. In here, there is a uniform prior in omega lambda, while in here, there was a uniform prior in basically the position of the first peak. Everybody's happy? Okay. Now, a question for you. This is obviously a problem because you present more data, you present towards constraint, and you go to your funding agency, and your funding agency says, give me back the money, right? And forget about money for your next experiment. So, at what point would a problem like this become less of a problem? Now, that's really useful for your funding agency, at least for you when you go in front of your funding agency.
Maybe if you have more data.
Right. At some point, the data overcome the prior. So you should go to your funding agency and actually say, but look, you actually need to give me more money because I need more data, because I want to know what the data tell me, not what the prior. So now we try to move on into modeling of data and statistical inference. I mean, we want to know how those people manage to put some constraint on omega lambda and omega lambda. And I suggest to read the numerical recipe book, chapter 15, and then we read it again. And in case you will ever apply any of this, just read it again. Alright, so let me make you an example that maybe you went through when you were doing any kind of labs, in your undergraduate or maybe even at school, and I'm sure you know how to solve the problem, but maybe you don't know why you're solving the problem that way. So let me go through this example. So you have some point, that's the x-axis, that's the y-axis, those are your data points. Each data point has got associated one error. You have some number, and you say the data is that, plus or minus this number. Whatever that means. We're going to discuss it later. And then you're being asked to fit this with a line. Do you remember how you do that?
Regression.
Right, and what do you do when you do regression? But then fitting means that you
have to use a guess.
right, so that's the model, it's a line. Right. Y is equal ax plus b. And the points have some error bar associated to it. So do you remember which equation you just take and plug there and get your result for those A and B? So you want to use least square. Is that what you're trying to do?
Yeah, kind of.
Okay. How many would do this with a least square figure? How many would do that with something more complicated? How many would draw a Markov chain Monte Carlo on this? That's probably the wrong tool, what do you think? Since you are estimating two parameters, but we'll come to this later. Okay, so you say, I do least square, and so you do least square, but then you also need some sort of figure of merit. Imagine some error or some data has got a very large error bar, and some other data a very small error bar. You may want to consider those two data points a little bit differently. At that point, if one has a bigger error bar and one has a smaller error bar, not all data points are created equal. So what you want are some basic parameters, some error estimates on the parameter, and hopefully, if possible, some sort of statistical measure that it tells you, are those really following a line, or maybe it was a cosine and I'm trying to, maybe the point will go like that and I was trying to fit that in the line. So, if you are a Bayesian, you say, what's the probability that a particular set of parameters is correct? What's the probability that A1 and B3 is the correct answer? And the figure of merit says, given a set of parameters, this is the probability of 4. So you maybe remember the least square fit looks something like that. If these are some weight, these are the value of the measurement, this is your model, and these are the parameters, and in the case of a line, these are if y is equal ax plus b, this alpha is a vector of two numbers a and b. So you can show, and Alan will go through this, that the minimum variance weight are 1 divided by sigma I, so this one should be an I, as the inverse variance weight. What if the data are correlated? You remember what happened in that case? Anybody remembers? Somebody has an answer. Yes. So if the data are correlated, then I cannot just give you one number for each data point telling me that's its error, because that's not sufficient information. I should give you also another number that says this point is related to the other ones, and that's probably going to be more than one number because it depends on how many points you have. It's related to this neighbor by this value, and to this is the next door neighbor, and the far away neighbor by another value. So in this case, you need a covariance or the inverse of the covariance. The covariance should go to the inverse of the matrix, or invert the independence, something like that. And you will recognize this symbol. It's chi-squared, so I'm sure that by now something brings back to mind and say, yes, I did chi-square when I had to fit some result from some laboratory experiment. Okay. So goodness of fit, maybe you have to report that. If all is Gaussian, then the probability of that chi-square at the minimum follow a chi-square distribution with some degrees of freedom, where the degrees of freedom are the number of data points minus the number of parameters you're trying to estimate. And the probability distribution is given by this gamma function. And either you punch that to the computer, that's the minus that. And then from that, you can also quantify somehow the goodness of fit if you evaluate this at the best value. And I probably did that in your lab. But then the question is, where does this come from? Why is this the recipe? Also, you may remember that you don't just report a result, you need to report some error bar around the result. So in case of this fitting, you report A and B, you need to report some confidence interval or confidence regions around the A and B value to be found. So the recipe that you had was if I pick the number of hidden parameters, which you want to plot the joint confidence region, and P is the confidence region desired, find the delta chi-square such that the probability of the chi-square variable with that piece of field of n less than what you measured is P. And then you do that with the function, or you just go to a table and you say 68% of 3 if you have one parameter is that, probability of 3, and this is your delta chi-square. Okay, so seems like a cooking recipe which works. Where does it come from? Before we go on, I want to define what are credibility intervals of variable regions. So Bayesian's intervals treat their bounds are fixed and the estimated parameter as a random variable, while frequentist confidence region treat their bounds as a random variable and the parameter as a fixed variable. That goes back to what Alan was explaining, the difference between the two, Bayesian and frequentist approach. But if we are doing statistics seriously, right, we don't just use a cooking recipe of the chi-square and just report that. We have a likelihood and we have a posterior, so we can use those. In many cases, we'll see later why. One can say that the likelihood is a multivariate Gaussian. Now, if you don't remember how a multivariate Gaussian is written, this is how the multivariate Gaussian is written. So that's your data, that's the prediction of your model, and that's the inverse of your covariance matrix. And it turns out that the covariance matrix is this. Now, do you understand where the chi-square come from, right? You see some gaps? Do you recognize this bit here? What's that here?
It's -2 less likelihood. -2 logarithm of
But this bit was the same thing as the chi-square. So that's where the chi-square come from here. Now, if you have a posterior, and you are a Bayesian, if you want to give some confidence region around the quantity that you've measured, what you do, you integrate your probability distribution for parameter given the data over the parameter range until you get to the desired level, 0.683, 0.95, or whatever. Now, there's the integration involved because now I'm treating the parameters as random variables. While the classical, you just take the ratio of the likelihood and you say, well, this has got to be below the threshold. So from the best fit, I go away only as much as this ratio does not far away from the max value. Now, these two are not necessarily the same thing. Remember the example that Alan showed at the end of his presentation? So if you have done that with the VSA plot, the one of the prior only, but with the node, they just told this is the posterior, right? You could have done that, and that's what they got. They got those plots for 68, 95%, etc., etc. Now, if you had done this instead, what would you have found? So imagine somebody that give you two columns, right? Your parameters, then one column is a function of the parameter, the likelihood, and in another column a function of the parameter, the posterior, the one that was shown in the first plot. So, what do you have found from this?
In the second one, the parameters are fixed, so we use this answer. Right. In the second one, the parameters are fixed.
So this one of the maxima. Let's go one step back. To produce the first posterior, what did they do? They kept the likelihood fixed and they just explored the value. And now they give you two columns, the posterior and the likelihood. And then if you don't know anything else, you just say, oh, this is the posterior, let me find 68%, 95%, and you produce those results. But if you do this, since this has not changed, this is always 1 or 1, then this will tell you there's no information there. Indeed, there's no information there, but it's just different. So these two things don't need to convey the same information, and they don't.